Hello students, in this video lecture I am going to discuss the concept of chain and anti-chain in PO sets. The first question arises is, what is a chain? Now we already know what a PO set is. Now before we talk of a chain, one should know what a PO set is. Although I have discussed the definition of PO sets in my earlier video lectures, but just to recall the definition of a PO set. Now when you are talking of a PO set, then you should have two things in hand. The first thing is that you should have a set. Let's say that set is P, some underlying set must be there, we are calling it as P, and some binary relation must be defined on that set, and that we are denoting by less than equal to sign. Now once you have these two things in hand, then P is said to be a PO set with respect to the relation less than equal to if three conditions are satisfied. And what are those three conditions? First of all, reflexivity must be satisfied. The second is antisymmetry must be satisfied, and then last thing is that transitivity must be satisfied. Now the question is, what is reflexivity? Now reflexivity is that if you pick up any element A belonging to P, then we must have that A must be related to itself. So for all A belonging to P, this condition must be satisfied, that A is related to A. So every element must be related to itself. This is what is called reflexivity. If this is satisfied, we say reflexivity is satisfied. Then coming to what is antisymmetry? Now for antisymmetry, you pick up any two elements A and B belonging to P, and let's say you have that A is related to B and let's say B is related to A. Let's say these two conditions are satisfied. Then if these two conditions together imply that A is equal to B, and if this happens for all such pairs for which these two conditions are being satisfied, then you say that antisymmetry is satisfied. So this is the second condition for a set P to be a PO set, and the last condition for a set P to be a PO set with respect to the binary relation less than equal to is that if you pick up any three elements A, B and C belonging to P such that you have A is related to B and B is related to C, then this must together imply that A is related to C. That is, first is related to the second and second related to the third. This together should imply that first should be related to the third. If such a thing happens, then you say that the condition of transitivity is satisfied. Now if for a set P less than equal to, if for a set P and for the relation less than equal to, if these three conditions are satisfied, reflexivity is satisfied, antisymmetry is satisfied, and transitivity is satisfied, then you say that P is a PO set with respect to the binary relation less than equal to, or P is a partially ordered set with respect to the relation less than equal to, or sometimes we even call it in short as a ordered set. So that was something about PO sets, which I have already discussed in my earlier video lectures, and in details we have taken that. But once you know that P less than equal to is a PO set, now we move a step further. When we know that it's a PO set, we just consider a structure which has an additional condition than a PO set. So already we have a PO set in hand. Let's say that PO set is P less than equal to, where less than equal to can be any binary relation defined on P. Now once you have this in hand, when do you say that P is a chain? When do you call it a chain, or when do you call it a linearly ordered set? This is another name for a chain. Or when do you call it a totally ordered set? These are different names for the same thing. When do you say that a PO set is a chain or a linearly ordered set or a totally ordered set? We say that a PO set P with respect to the binary relation less than equal to defined on it, or now it's a partial order relation defined on it, then P is said to be a chain if every element in P is related to the other, which means that if I pick up any two elements, if I pick up a pair of elements, any arbitrary pair of elements belonging to P, then this must imply that X must be related to Y, and this should happen for all the pairs X and Y belonging to P that I choose. If such a thing happens, then you say that P is not only a PO set, but it's rather a chain or a linearly ordered set or a totally ordered set. So in a way something like this has happened. If you pick up an element and if you pick up another element, then there is a sort of relation between them, there is an association between them. Then if you pick up another third element, then again there is an association between the two elements. If you pick up another element and if you compare this with this, then again you will find there is some kind of association. So a sort of chain in the real sense would be formed, or a linearly, this is a sort of line that would be formed. That is why the name comes chain or a linearly ordered set. So that was the definition of a linearly ordered set or a totally ordered set or a chain. Now just coming to a few examples, when is a example of just a few examples we would be taking of a PO set which is a chain and of a PO set which is not a chain. So let me start with the first example, a simple example in which you will see that the PO set will come out to be a chain. So let me take the set of real numbers and let me define the binary relation less than equal to on it, where this less than equal to means the usual less than equal to relation, the usual sense in which we understand less than equal to sign, which means that I know that for two real numbers A and B, A less than equal to B will be true if either A is strictly less than B or if A is equal to B. Now we have already seen, and in my earlier videos you can watch those videos just to show that this particular set is a PO set. Otherwise also you can verify, even if you don't see those videos, you can verify it for yourself, that with respect to the less than equal to sign, you can just see that every real number is related to itself. Then so reflexivity is satisfied. Then reflexivity is satisfied, antisymmetry is satisfied, because if you pick up any two real numbers such that A is less than equal to B and B is less than equal to A, then where less than equal to means less than equal to in the usual sense, then we know that A is equal to B. And if you pick up any three real numbers A, B and C belonging to R, then such that A is less than equal to B, B is less than equal to C, then we know that A is less than equal to C. So transitivity is satisfied. So all the three properties are satisfied: reflexivity, antisymmetry and transitivity, which means that this is very much a PO set or a partially ordered set. But besides being a PO set or a partially ordered set, it is not just the set of real numbers is not just a PO set, but it is also a chain rather, because if you pick up any two real numbers, any pair of real numbers, if you pick up, I can always compare them. They are always comparable, they are always related, which means that either A will be less than equal to B or B will be less than equal to A. That we know, where less than equal to means less than equal to in usual sense. So either A will be less than equal to B or B will be less than equal to A, which means that every pair of real numbers will be related to the other, and in that sense every element is related to the other. So in that sense it becomes a chain. So R less than equal to is an example of a PO set which is a chain. So this was the first example in which a PO set is a chain. Let me take now the second example in which you have a PO set which is not a chain. For example, if you take P to be, let's say, the power set of a set X, where X is any set, X can be a set which is any set. If the structure of the set capital X is not important, it can be any set. And what you do is you take P to be Px, which is the power set of X, which means that this is the set of all subsets of X. Set of all subsets of X. To make my example precise, I will take precise structure of X, but we know already, we have discussed this already in my previous lectures. You can see the recordings. In that we have already discussed that the power set of X with respect to the inclusion relation is a PO set. This set is a PO set, where what does this inclusion relation mean? This inclusion relation means is subset of or is contained in, which means that if you pick up any two A and B belonging to the power set of X, because power set of X consists of all subsets of capital X, so these two are subsets of capital X, or they are sets themselves. So you will say that A is related to B if A is contained in B. So this is how, or if A is a subset of B, or if A is included in B. So this is the inclusion relation, and we have already seen that this is a PO set. Now to be precise in this particular example, let me take my X to be 1, 2, 3. You can choose your X to be anything. And I'm taking my power set of X in that case, because this has 3 elements. Whenever the number of elements is 3 in a set, then the total number of elements in the power set of X, which means the total number of subsets of X, is going to be 2 to the power 3, which is 8. So there are going to be 8 subsets of the set capital X, and those 8 subsets are phi, which is the empty set, which you can even write like this, and the set of 1 elements, which is singletons, 1, 2, 3, then the set of 2 elements, 1, 2, 1, 3, and you can write the next element is 2, 3, and then the last set is 1, 2, 3, which is the set X itself. Now you can just see that this set, the power set of X with respect to inclusion relation, this is a PO set. We already know it's a PO set. Because whatever the set capital X may be, we know that this is a PO set, but you will see that this is not a chain. This set is not a chain, because we will see that not every pair of elements in power set of X is related to the other. For example, if you pick up 1 and let's say 2, these 2 singletons, if you pick up, these 2 are elements of power set of X, but you can see that 1 is not contained in 2, and 2 is also not contained in 1. So that way, from these 2 relations, we have that 1 and 2 are not related. They are non-comparable. So we have found a pair of elements which are non-comparable. They are non-related. So this is not a chain. Instead of taking these 2 singletons, I could have done the same thing. I could have given the same argument by taking let's say 2, 3. These 2 are elements of power set of X. So this is the singleton element consisting of just 1, and this is the set consisting of 2, 3. And now you can see that 1 and 2, 3, these 2 are again not related to each other, which means that we have got a pair of elements in the power set of X which are not related to each other, which means that that this particular PO set, power set of X with respect to inclusion relation, although this is a PO set, but it fails to be a chain. This is not a chain. So we have seen 2 examples. One example which is a simple example of a PO set which is a chain, and second example which is the example of a PO set which is not a chain. So these are the 2 examples which explain the concept of chain. Now one important thing which has to be noted in this regard is that if you have a PO set, let's say P, and let's say the partial order relation defined on it is less than equal to, and Q is a subset of P, then we have already seen that Q less than equal to is also a PO set with respect to the induced order. This less than equal to is same as this less than equal to. So we have seen this already in the earlier videos. You can see that subset of a PO set is a PO set with respect to the induced order or the inherited order. This binary relation or this partial order relation remains the same. So now I move a step further and I say that if P less than equal to is a PO set, and if it is not only a PO set but let's say it's also a chain, in that case if Q is a subset of P, then Q less than equal to will not only be a PO set but Q less than equal to will also be a chain with respect to the induced order or inherited order, just because the elements of Q are finally the elements of P, and the elements of Q behave in the same way as the elements of P. So if elements of Q P are related to each other by less than equal to, the same way the elements of Q will be related to each other. So if you pick up any 2 elements over here in P, they will always be related, and the same way the elements of Q will behave, because Q is finally contained in P. So this gives me an important result that a subset of a chain is a chain. So this is one important observation that we have from here regarding chains. Now coming to the next concept, which is the concept of an anti-chain. Now the question arises, when is a PO set said to be an anti-chain? Now a PO set P less than equal to with respect to the partial order relation less than equal to, this PO set is said to be an anti-chain if every element is related to itself. Which means that if you have if every element is related just to itself, this is the definition of an anti-chain, which means that if you have that for x and y belonging to P, if you have that x is related to y, then this is possible only if x is equal to y. So every element is just related to itself. So this is the definition of an anti-chain. And now the examples in this regard, again I am going to take an example of a set which is an anti-chain and a set which is not an anti-chain. So in the first example, let me take my set P to be 1, 2, 3, consisting of 3 elements, and let me define relation less than equal to on P as for A and B belonging to P, A is related to B if you have A minus B is equal to 0, or you have A is equal to B. And this is actually this relation we have seen, we have given a name to it. This is discrete order, and we have seen with respect to discrete order this particular set P less than equal to, this is a PO set. We have seen that. In fact, we have given a general result that with respect to this particular relation, if you define your binary relation to be this, then any set P becomes a PO set. So and of course you can also prove this also, that this is a PO set because the 3 properties reflexivity, antisymmetry and transitivity are satisfied, because whatever element A belonging to P you may choose, A minus A is going to be 0, so A is related to A, which means that reflexivity is satisfied. This is the first property. Then this happens for all A belonging to P. Then again antisymmetry is satisfied. Why? Because if you pick up any 2 elements A and B belonging to P such that A is related to B and B is related to A, then by definition of less than equal to, A minus B will be 0 and B minus A will be 0, which means, and transitivity is also satisfied, because if you pick up any 3 elements A, B and C belonging to P such that what happens, such that you have A is related to B and B is related to C, then here by definition of less than equal to, A minus B is equal to 0 and B minus C is equal to 0, which means that A is equal to B and B is equal to C, which actually means that A is equal to C, and which means that A is related to C. So A related to B and B related to C, first related to the second and second related to the third implies first is related to the third. So all the 3 properties are satisfied: reflexivity, antisymmetry and transitivity. So with respect to this particular relation less than equal to, which is defined like this, that A is related to B if A minus B is equal to 0, or if A is equal to B, this particular with respect to this particular relation P less than equal to, this is a PO set. And as I already said that if you have P to be any set of any type of elements, if you define this particular relation on it the way I have defined over here, then P less than equal to will always come out to be a PO set. And this particular relation, as I already mentioned, this has a name, it is called a discrete order. So with respect to the discrete order, every set can be made a PO set. Also, this is not the, in this case P less than equal to is not only a PO set, but it is an anti-chain, because it is satisfying the property of an anti-chain, because the relation is precisely defined like this: for A and B belonging to P, A is related to B if A minus B is equal to 0, or if A is equal to B. And this is nothing but precisely the definition of an anti-chain. In an anti-chain, such a relation is satisfied, that every element is just related to itself. If 2 elements are related, then this means they are equal. So every element is just related to itself. So this is an anti-chain. So so P less than equal to here not only comes out to be a PO set, but it also comes out to be an anti-chain. So a general remark or a general note which can be made in this context is that given any set P, not necessarily this set of 3 elements 1, 2, 3, because as such they are not playing any role. Given any set P, you can make it a PO set by defining discrete order on it, which means this particular relation which I have just written, and also you can make this set P an anti-chain by defining the discrete order on it. And generally we are in the habit of representing anti-chain by P bar. If P is the set, then P bar is the P bar. This represents the anti-chain P bar. So that this was an example of a PO set which is an anti-chain. And now coming to one last example of a PO set which is not an anti-chain, which is the same example, the same second example that we took for a chain. I took my X to be 1, 2, 3 in the second example when we were considering chains, and then we had seen that power set of X with respect to the inclusion relation. This PO set, we had seen that this is a PO set where power set of X is the set of all subsets of X, and this consists of 2 to the power 3, which is 8 elements. We have discussed this already. And now this particular PO set, we had seen in the example above that this is not a chain. And now what I'm going to tell you is that this particular PO set is not even an anti-chain, because we have seen, you can see the elements of the power set of X are over here. Let me go back here. If you pick up these two elements, 1, and if I pick up this one, 1, 2, these are two elements of the power set of X, then you can say that, you can see that they are related, because this is contained in this. 1 is contained in 1, 2, but is 1 equal to 1, 2? No, 1 is not equal to 1, 2, which means that if two elements are related, then it's not necessary that they are equal, which means that unequal elements can be related, and this should not happen in an anti-chain. So this is not an anti-chain. So here we can precisely write what makes because of what Px is not an anti-chain. Now here Px, the power set of X with respect to inclusion relation, this is not an anti-chain. This is not an anti-chain. Why is it not an anti-chain? It is not an anti-chain because you have that if you just pick up 1 and 1, 3, let's say, or 1, 2, whatever, both of them are elements of power set of X, but you can see that 1 is related to 1, 2. Why 1 is 1, 3? Why you have taken 1, 3? 1 is related to 1, 3 because this singleton is contained in this, but you can see that these two elements are not equal. This means that unequal elements can be related, but in an anti-chain, every element must be related only to itself. Unequal elements should not be related, but here unequal elements are related, and you can take any such pair like this. It's not necessary that you have to take this only. I could have taken the pair 2 and 2, 3, something like this, and 2 is contained in 2, 3. So this pair also gives you tells you the fact that this is not an anti-chain. So power set is an example of a PO set which is not a chain and which is not an anti-chain. Now an important note in this regard is that if you have, in general, a note I am giving the same way that as I had done with a chain. If you have P less than equal to is a PO set, and if you have Q is a subset of P, then as already said that Q less than equal to will be a PO set with respect to the induced order. This is the this order is this less than equal to is the induced order. It is the same order as this. Now what I'm trying to say is I'm moving a step further, and now I say that if P less than equal to is a PO set and if Q is a subset of P, then Q less than equal to is not only a PO set with respect to the induced order, or inherited order, but if you have that if this P less than equal to if this P less than equal to, if this is an anti-chain, then this Q less than equal to will also be an anti-chain. Why it will be an anti-chain? Because the elements of Q are the elements of P, as Q is contained in P. So whatever properties the elements of P are satisfying, the same properties the elements of Q are satisfying, because the order is the same. The order is the induced order or the inherited order. So if P less than equal to is an anti-chain, then so is Q less than equal to. So that is the important remark in context of anti-chains, and that completes the topic on chains and anti-chains.